Hey guys, so this is section 1.3, rates of change and behaviors of graphs. We're going to see three major ideas in this one. We're going to see average rate of change first, and then something called the difference quotient, and that's another rate of change thing. And behaviors of graphs, we're just going to do a little bit with increasing, decreasing, and constant at the end. So starting with average rate of change. So we have this green graph right here. If you can see, it's this curved one. And on the green graph, there's these 2 points, A and B. And so what this is for the green graph, if I drew the line through those 2 points, the slope of this line, remember that's change in y over change in x. So the slope of the blue line right here going through those 2 points is the average rate of change. So what we're finding when it says find the average rate of change is the slope between 2 points on a curve. And so this is our average rate of change formula, which looks a little tiny bit threatening maybe. But if we can kind of figure out how it corresponds to our slope formula, it makes it, I don't know, at least a little bit more understandable. So if this is A, back in the old days, that was our x1 and our x2, right? And then this would be like our y1 and our y2. And so these points are, x1, y1, x2, y2. And to find our slope, we would go y2 minus y1. So in the average rate of change formula, it's f of b minus f of a. And then the denominator, the denominator was x2 minus x1. And so here we have b minus a. And so that's just basically function notation version of the slope formula. Okay, so for the first problem we got, given this function, find the average rate of change from 1 to 3. Okay, so here's 1, and here is 3. And so if I attempt to draw a straight line, which will be suspect, but here it goes. Not too bad. So the slope of that line, approximately for my line, is going to be our average rate of change. And so just looking at the graph, right, we can just look at this thing and know what it's going to do. If we draw our triangle, it's going to go over 2, it's going to go up 4, and so it's going to be 4 and 2, so that's our rise and our run. And remember way back when we had rise over run was m, so m's going to turn out to be 2. If I look at this another way, so this point right here, this is 3, 4. And this point right here is 1, 0. So remember how when we did slope y2 minus y1, x2 minus x1. Okay, so in this case, if we go, actually let me write them right here, 1, 0, 3, 4. So if we just take these 2 points and chuck them in the slope formula, then we should get the slope, which should be 2. So let's see, y2, y1, so 4 minus 0, and x2 and x1. And there's that same 4 over 2 again. So now, find the average rate of change from 1 to 3. Our formula for average rate of change is, and I'm just going to abbreviate that, average rate of change because it's way too much to write, is f of b minus f of a over b minus a. And so this function, that's that green line, and what we're trying to do is essentially that math to it. And from 1 to 3, so this is from a to b. So then we're just going to evaluate this at 3, and so that would be f of b. Actually, I'm going to write right here, f of 3 minus f of 1 over 3 minus 1. So f of 3, we'll just toss a 3 in here. That's going to be 3 minus 1 squared, and then minus f of 1. So f of 1 is going to be 1 minus 1 squared over 3 minus 1. Cleaning that up, I get 2 squared minus 0 squared over 3 minus 1. And you can see right here, it's the exact same thing as the slope formula, right? because this is going to come out 4 minus 0 and 3 minus 1, so 4 over 2. So average rate of change is 2, so is the slope, exact same thing. So hopefully that one gives you a little bit of an idea, at least what average rate of change is. You're going to see this one a bunch in calculus, and likewise with the difference quotient coming up. The difference quotient and this are similar from your perspective right now. Average rate of change stays in the land of algebra, and then the difference quotient ends up being kind of the definition for first quarter calculus. So these are pretty important topics. Okay, so for number 2, we're asked to find the average rate of change for 4x cubed, and that's going to be from -2 to b. So our a and our b this time are, one's a number, but the second one's going to be a letter. And so that means we're going to get basically some equation that we could plug values into that would find the average rate of change, because this is like from -2 to some point to be named later, and so we can allow that to vary by changing that input. But anyhow, so don't expect to get like a number answer. It's going to be an equation. So let's see, f of b minus f of a, so that would look like b is b, so that's going to be f of b minus f of -2 over b minus -2. F of b would just be a variable change, so 4b cubed, and then f of -2 would be 4, and then -2 cubed over b minus -2, so that'll be b plus 2. Cleaning this up a little bit, I'm going to get 4b cubed minus, this is -8 times -4, so that'll be plus 32 over b plus 2. And then this factors and cancels, and so if you need a refresher on the cube formula that's coming up, it's going to be section 5.5 in 094. And if you need a general review of factoring, 5.6, also 094. And this one I go through all 6 methods. So if you have a little bit of weakness in factoring, or it's a skill we're going to use a lot in the course, so not a bad one to go back and spend a couple minutes and review. So for right here, I can take out a 4, b cubed plus 8 over b plus 2, and then this is that cube formula, so it goes 4 and then breaks down to b plus 2 and then b squared. B times 2 would be minus 2b, 2 times 2 will be a 4. And if that was mysterious how I just did that, go back and check out 5.5 over b plus 2. Cancel those, and then what's left would be the average rate of change. Okay, same basic problem, except this time it's going to go from x to x plus h, and this is our function. So this is going to look like, let me write out the function notation for this one. F of x plus h minus f of x. So there's f of b minus f of a all over b minus a. And what this turns out to be in just a second is the difference quotient for the next set of problems. So setting this up with this formula, this is going to look like, so if I have f of x plus h, it just means that x plus h is going in for that x. So that'll look like 3 x plus h squared minus 7. And minus f of x is just the original formula. And that's all over x plus h minus x, but those x's cancel, so it's just going to be over h. This is that binomial square that I'm going to expand, talked about a couple videos ago. So x squared plus 2xh plus h squared, and minus 7. And then distributing the negative through, I'll get negative 3x squared and plus 7. And if you're not great at that, you can also just run them side by side, right, and do FOIL. I'm going to run the, over h. There we go. I'm going to run the 3 through. And copy all the rest of this. I only put the 3 on that. That's brilliant. Here we go. And then we can do some canceling. So I got plus 7 minus 7 plus 3x squared minus 3x squared. And I always tell people to rewrite what's left because this can get kind of messy and hard to see. So if I do that over this, and now the h should go into both terms, which it does, but that will always work. And so that would be our average rate of change. Okay, so number 4, we got a fraction. So we're going to do our same thing. It's going to be that f of x plus h minus f of x, and then over x plus h minus x. So with this function, that's going to look like 1 over x plus h minus 5, and then minus the function, all over, and then remember the x's cancel, so that's just going to be h. And then this is a complex fraction, and we saw those in Math 95. And in the old book, it was section 8.4. In the new book, it's section 7.4. And what we did there was we used the LCD to clear the fractions. And so all I'm doing is multiplying it by 1, because this would just be, it's the same thing over the same thing, so that's just a 1. If it helps to think of it like this, that's not the worst thing. I'm just making it seem like a fraction over a fraction. But with the 1s there, you can kind of see here, this is just going to multiply the h. Here, this is multiplying the 1s, and then what's going to happen is it's going to cancel. So if you picture this thing up in both these numerators, and then here we cancel the 3 term, we'll be left with this. Here we'll be canceling the 2 terms and be left with that. So what that's going to look like is 3 terms cancel, so 1 times x minus 5. And this is the minus from right here. And anytime we do a minus, we want to open a parenthesis. So if this is right here, these are canceling, leaving the 3 terms. And then that's all over this big mess of math. So it's going to be h x minus 5. And then these don't cancel, right, because this isn't factored, so we got to collect terms. So up top, that's going to be x minus 5 minus x minus h minus a minus, make a plus 5. And I'm just going to write LCD down here to not write all that again for a second. And then we got plus x minus 5 plus 5. So that's going to just leave negative h. And now I need this stuff. Because now you can cancel those. And then to write the answer, when the whole numerator gets canceled, I can't just have like a floating negative sign. So it's negative 1 over that stuff that's left. So that formula that we kept getting back here, where we'd plug in f of x plus h minus f of x all over h, when we did the average rate of change from x to x plus h, that's actually the difference quotient, which is our next topic. And so here we have this value x right there, and then this distance is h from here to here. And so if this is x and this is h, then this would be x plus h. And the idea is when I put in x, I get out an f of x. When I put in x plus h, my y in function notation is f of x plus h. So if I go y2 minus y1, there's my numerator, x2 minus x1, and remember that's when those x's kept canceling, there's the denominator. And so this is going from, instead of saying having kind of 2 fixed points that we're looking at, this is saying we're going to have some value x, and then we're going to let this distance vary. And what that does is this is where it kind of becomes calculus. But instead of just finding the average rate of change between these 2 points, I can let this point get closer and closer. I can let h go to 0 and get smaller and smaller until I basically, this thing would flatten out and I would get a tangent line right there at that point. And it would give me what's called the instantaneous rate of change at a single point. And when we go from average to instantaneous, that's where it's going to become calculus in a couple more quarters. In this course, we're mostly using it for practice with some function notation. So find the difference quotient, which is the f of x plus h minus f of x all over h for this function. So we're going to go x plus h in for these x's first. And we're going to subtract the original function. So that's just this. And got to open that parenthesis, super important. And then that's going to all be over h. And then these ones do a couple of things. As we expand them, we're going to find all the stuff is going to end up canceling, and this h is going to end up dividing into what's left. If those things don't happen as you're solving it, it means like a sign's gone bad somewhere or you have some sort of trouble. So first I'm just going to expand the squared, distribute the 2. So this is going to be 3, and then this is that same form again, so that's x squared plus 2xh plus h squared. Distributing there, I'm going to get plus 2x. There's something where people forget the 2 on the h, so a good spot to look for errors. And then running the negative through, I get negative 3x squared minus 2x plus 7 all over h. And then I still have to do the 3 through this set. 6xh and 3h squared. Okay, so now we got that big wad of math. And so here's the canceling that should happen. Everything that was in f of x plus h should cancel with something earlier. So minus 3x squared plus 3x squared minus 2x plus 2x plus 7 minus 7. If that doesn't happen, again, you got a sign wrong somewhere or something went wrong. The second thing that should happen, and I'm going to rewrite what I have left just for kind of for clarity. So the second thing that should happen is there should be an h in every term that allows me to cancel out this h. So it's like I could factor an h out of the top and then cancel h over h. I'm just going to kind of think of it as 3 cancels. But so here the h should be gone. 2 up, 1 down, so it's going to leave plus 3h. And those would cancel, leaving a 2. So this is the difference quotient for that function. And in calculus, this is going to end up being what's called the derivative of that function, or just about pretty close. We'd have to do something with the h. But yeah, very, very close to first quarter calculus here. So this one's similar, but now we got a fraction again. So we'll do f of x plus h. So that's going to be x plus h right there, plus 4, and then minus f of x, the original, and then all over h. And then this, I'm going to rewrite this piece as with this distributed through, I think. Yeah. Actually, I'm not going to rewrite it because I'm going to run out of room on the paper. But you can see it's going to be 3x plus 3h. So as I clear my fractions, I'm just going to write it that way. So this and that are the same. And that's all over the same stuff. And again, if you find it helpful to think of all that as kind of over 1, and those as over 1, just to kind of see how things line up. It can be useful. So here, remember, this and this are the same. So if this is up here, because that's just a distribute, then the 3 term would cancel. I'm left with the 3x plus 4. And minus here, the 2 terms would cancel. And I'm left with minus this stuff. So I'll show it with the parenthesis. And that's all going to be over. I'm just going to write, for this stuff, I'm just going to write LCD for right now, but it's h times that. It's just a pain to write it over and over. Let me distribute the negative through. And then let's see, if we cancel, we're going to get rid of the x's and the 4's. And so we're just left with the negative 3h up top. And then I'll bring this back now. You might have noticed I just changed the order that I'd written them up here. Usually when they're down in the denominator, they usually go 2 things by 3 things, but there's nothing wrong with writing it the other way. This would just be a little more standard. And then from there, you can just cancel those h's, and then negative 3 over this would be our answer. So our last topic was regarding the behavior of graphs, and it's increasing, decreasing, constant. Basically, a graph is increasing if, as you're going left to right, it's going up, and decreasing if it's going down, and constant would just mean it remains at sort of a fixed value. Where people have some trouble with this is in terms of how to write the answers. So increasing, decreasing, constant are reported in terms of the intervals in which the behavior is occurring. In other words, the x values, not the y values. So if we have some function, we're not saying it's increasing from here to here, we're saying it's increasing on this range. So for instance, if I had something that looked like this, I'd say it's increasing on the interval AB. And if I had something like that, I would say it's decreasing on the interval BC. And then something like that would be constant on the interval CD. Local maxima and minima. So this is a lot of math words, but basically what it's saying is if I look at some interval, say from here to here, and there is nothing bigger than that point, then that point's called a local maximum. If I look on an interval and there's nothing lower than that point, then that point is called a local minima. Okay, so this last example is find where the function is increasing, decreasing, constant, and if it has local maxes or mins. So increasing, let's do this in colors. Increasing would be from right here to right here. It's getting bigger. And so what we don't want to do is say it's increasing from -2 to 3, and that's what people want to do. We want to say it's increasing on the interval -4 to 0, because this is where the behavior is happening. And likewise, it's increasing, it hits a low point here and then starts coming back up. It doesn't matter that it's negative, it matters that the slope itself is positive. So if you think of the slope of this line, that's positive. The slope over here is positive. So that's going to be happening right through there. So what I have, those little lines right there, is what I need to say for my answer. And then technically at the turning points, the slope right there is 0. It's flat. The slope was negative, it does something, and then it's positive. The only thing you do is go through 0. So we can't include these endpoints ever when we're doing increasing and decreasing or constant. So we're going to go from -4 to 0, and then union from 4 to 6. And then let's see, for decreasing, that's these other areas. So all through here it's getting smaller. If I look at the slope would be negative there. So this is going to be decreasing, and likewise from here to here is going to be decreasing. So this is going to go from -6 to -4, union 0 to 4. Constant, we don't have an interval where it does that. We do have a couple of points where it's doing that, but that's that first quarter calculus thing again. So we'll just say none. And then for our max, that would appear to be right there. Just going to show it as an ordered pair, saying the maximum occurs at 0, 3. Sometimes you'll see where a book will separate to the max occurs at 0 and the value is 3. I'm just giving it as an ordered pair. And then there are minima. So it's going to be -4, -2, and 4, -2. And then for this one, let's see, we're increasing from here to here. It's right there. So that's from -6 to -3. And this all decreasing, bottoms out here, starts coming back up. And so, right there, union 3 to 6. Decreasing is happening on the whole other, so all this is getting smaller and smaller. So that's all between here and there. So it's going to be from -3 to 3. And then again, no constant. The maximum occurs right there at -3, 3. And this one has a local min at 3, -3. And that wraps up rates of change.